Welcome. We are entering a defining era for national security and corporate resilience. The race toward Q-Day, the moment quantum computers can bypass traditional encryption, is accelerating. From the 2018 National Quantum Initiative to upcoming 2026 executive mandates, the message is clear. Transitioning to quantum-resistant infrastructure is now a strategic imperative. Today, we'll discuss how to align your commercial roadmaps with these critical policy shifts to ensure your organization remains secure in a fault-tolerant future. The U.S. government is currently executing a vital two-pronged strategy to master the quantum era. We are aggressively mobilizing private industry and federal agencies to develop the world's first error-corrected quantum computer, the ultimate computational capability. Simultaneously, we are mandating a rapid transition to post-quantum cryptography. This dual mandate is about balance. We must build the most powerful tools in history while ensuring our cryptographic shields are ready before today's encryption becomes obsolete. The 2018 National Quantum Initiative Act served as the definitive catalyst for American leadership. Signed in December with a $1.2 billion commitment, it launched a unified strategy to accelerate R&D. By creating a central coordination office and funding major research centers through the Department of Energy and National Science Foundation, the Act bridged the gap between government, academia, and industry. This framework transformed quantum science into a strategic national priority. In June 2026, two landmark executive orders launched a dual-track strategy to master the quantum frontier. We are accelerating our innovation capability, aiming to deliver the first error-corrected quantum computer through a strategic 5-year roadmap. Simultaneously, we're fortifying national security. By mandating a transition to quantum-resistant encryption for all high-impact systems by 2031, we ensure our most critical data remains protected against emerging cryptographic threats. This is our definitive path toward quantum leadership and resilience. The quantum landscape is far more than just a race for superior hardware. It is a mobilized, three-tiered ecosystem where physical processors, cloud orchestration, and specialized software applications are deeply intertwined. Crucially, both federal and private funding are fueling this entire stock, rather than betting on a single player. This approach builds a resilient, interdependent supply chain, ensuring that progress in one layer accelerates the others, ultimately driving rapid iteration and collective success. The race for quantum advantage is a multi-front battle. While superconducting systems from giants like IBM lead in speed, they require extreme cooling. Meanwhile, silicon spin leverages existing semiconductor infrastructure, and photonic and neutral atom technologies offer promising room temperature scalability. Every modality faces unique engineering hurdles, whether it's photon loss or complex laser controls. Ultimately, these competing architectures represent a diverse toolkit aimed at solving the same ultimate challenge: achieving stable, scalable quantum computing. Quantum information is exceptionally fragile, making environmental noise our greatest physics hurdle. To run complex algorithms reliably, we must move beyond today's noisy hardware toward fully error-corrected systems. The challenge lies in the immense hardware overhead. It takes thousands of raw physical qubits to produce just a few stable logical ones. Mastering this error correction process is essential to meeting upcoming mandates and finally transitioning quantum computing from experimental theory into a powerful, dependable reality.
We are witnessing a pivotal shift in quantum hardware. We have moved beyond theoretical proofs to demonstrating real-world error correction. Over the next few years, the industry's focus shifts towards scaling qubit connectivity and system complexity. By 2029, we anticipate a massive inflection point: the arrival of fault-tolerant utility-scale systems. This marks our transition from managing experimental noise to achieving the reliable, error-corrected computation necessary to solve the world's most complex challenges.
We are racing against a cryptographic ticking clock. By 2029, advanced quantum computers will likely shatter the encryption standards securing our world today. This isn't just a future threat. Through harvest now, decrypt later tactics, adversaries are already collecting our data to unlock it once technology matures. To protect national security, we must act immediately. Migrating to post-quantum cryptography is no longer optional. It is a critical imperative to safeguard our past, present, and future data. The post-quantum cryptography mandate is a high-stakes race for national security. With strict federal deadlines approaching in 2030 and 2031, preparing your infrastructure is no longer optional. You must immediately inventory your legacy encryption for total visibility and build crypto agility to swap protocols without massive downtime. Most importantly, this migration cannot happen in a vacuum. It must be structurally integrated into your zero-trust architecture. Visibility, agility, and alignment are your keys to a quantum-resistant future. We are approaching a pivotal moment, the Q-Day intersection. By 2029, commercial hardware will likely achieve the power to break current RSA encryption. To counter this, government mandates demand full post-quantum cryptographic integration by 2030. This timeline isn't arbitrary, it's a calculated race. Our defensive shield is being mathematically reverse-engineered to match the offensive threat. We must be ready, because the weapon and the shield are set to arrive at the exact same moment.
To navigate the quantum shift, we must act now. First, perform an immediate crypto inventory. You cannot protect what you cannot see. We need to identify all vulnerable RSA and ECC algorithms across our architecture. Second, we must build crypto agility into our systems, enabling seamless transitions between cryptographic standards. Finally, leverage NQI Act consortiums to track emerging hardware modalities. Q-Day is no longer a theoretical horizon. It's a scheduled event. Readiness is now a strategic necessity. When we talk about executing probability, we are moving beyond pure mathematics into the realm of real-world engineering. Building the full quantum stack requires us to translate abstract theoretical concepts into precise physical hardware that manages the volatile nature of quantum states. This journey from theory to practice is the defining challenge of our era. Today, we'll explore how we bridge that gap, transforming complex probabilistic models into powerful, functional computing systems that redefine what's possible. We're witnessing a fundamental shift in how we approach complex problem solving. While classical systems are limited to navigating deterministic paths one at a time, quantum utility allows us to evaluate entire multidimensional probability spaces simultaneously. This is no longer just a laboratory concept. With technology readiness levels reaching 4 to 5, quantum hardware is moving into scalable cloud environments, ready to tackle the real-world challenges that were once considered computationally impossible. We often think of a quantum computer as just a chip, but it's actually a sophisticated full-stack translation engine. Your high-level code must journey through layers of compilation and digital-to-analog conversion before becoming the microwave pulses that control the hardware. This processor, kept at near absolute zero, relies entirely on a massive classical supercomputer to function. In essence, quantum power is orchestrated by classical precision, working together to turn abstract algorithms into physical reality. To truly harness quantum power, we use the Hadamard gate to create superposition. This operation transforms a definitive state into a wave of possibilities, where a qubit exists as a weighted combination of both 0 and 1. Mathematically, these amplitudes represent the probability of each outcome. By placing a bit into this state of equal probability, we move beyond binary logic, allowing the system to explore multiple paths at once. This is the heart of quantum computation. Think of quantum operations not as simple bit flips, but as elegant rotations in multidimensional space.
By combining a Hadamard gate with a CNOT operation, we move beyond individual qubits to create entanglement, the Bell state. Because the control qubit exists in superposition, the two particles become mathematically inseparable. From this point on, you cannot describe one without the other. They are a single, unified system, dancing in perfect quantum choreography. Quantum computing doesn't provide answers instantly. While qubits explore a vast superposition of possibilities, measuring them causes an immediate collapse into one random outcome. Because quantum mechanics is inherently probabilistic, a single execution is never enough to find the truth. We must run the exact same circuit thousands of times, a process called taking shots. By aggregating these results into a statistical distribution, the noise fades away, and the correct answer finally emerges as the clear, unmistakable peak. Let's apply these concepts to a practical challenge: building a quantum lottery machine. Unlike classical computers, which use mathematical algorithms to mimic randomness, this 6-qubit circuit leverages the fundamental unpredictability of quantum mechanics. By placing these qubits into superposition, we transition from predictable math to true physical randomness. This ensures our lottery numbers aren't just random enough. They are generated by the core laws of physics, offering a level of security and unpredictability no classical system can match.
Imagine the immense power of quantum superposition. By applying Hadamard gates to 6 qubits, we shift the system from static bits into 64 simultaneous realities. For a brief microsecond within the dilution refrigerator, our processor encodes every single value from 0 to 63 with equal probability. Instead of checking options one by one, the solution already exists as a ghost within this vast probability wave, waiting to be revealed through measurement. In the quantum world, measurement isn't just observation, it's an act of creation. Before measurement, a system exists in a state of pure probability. However, once we measure it, that superposition collapses. The wave vanishes, forcing the universe to choose a single, truly random integer. If we repeat this process 5 times, we produce a Mega Millions ticket generated not by computer algorithms, but by the fundamental and irreducible randomness of the universe itself. As we move from theory into reality, it's vital to understand that a singular quantum computer doesn't exist yet. Instead, we're in a fierce hardware race across various modalities. While superconducting circuits offer blazing gate speeds, atomic systems provide superior coherence. Every approach faces its own unique scalability constraint, from cryogenic heat to photonic loss. Success depends on how we balance these physical trade-offs to finally achieve reliable, large-scale quantum advantage. Take a look at the IBM Heron processor. At its heart is the Josephson junction, the essential building block of a superconducting qubit. By sandwiching a thin insulator between superconductors, we enable Cooper pairs to tunnel through, creating a vital non-linear inductance. This allows us to isolate 2 specific energy levels to represent 0 and 1. Through Manhattan-style fabrication, we achieve the extreme precision and consistency needed to scale these quantum systems across the entire wafer. To execute precise quantum operations, our control stock bridges extreme environments. It starts at room temperature, where processing units generate calibrated microwave pulses. These signals travel through shielded superconducting lines to the QPU, operating at millikelvin temperatures, colder than deep space. This extreme cold is critical. It prevents thermal energy from destroying fragile quantum states. By using quantum-limited amplifiers to capture faint signals, we achieve the high-fidelity control and measurement results demonstrated in our recent time scans. The ultimate challenge we face is decoherence. Qubits are incredibly fragile, susceptible to even slight heat or radiation. This noise rapidly degrades the quantum wave, leaving us a narrow window, defined by T1 and T2 times, to perform calculations. We are currently in the NISQ era, racing to finish processing before information scrambles.
Mastering this noise is the final hurdle to unlocking the full, reliable power of quantum computing.
To move toward practical quantum computing, we must embrace a fundamental paradigm shift: quantum error correction. Since we cannot copy quantum information, we entangle multiple noisy physical qubits into a single, highly stable logical qubit. Using the surface code, specialized qubits monitor their neighbors to detect errors without ever measuring and destroying the underlying quantum state. Finally, classical processors must decode these signals and apply corrections in microseconds. This synergy is essential for building reliable, fault-tolerant quantum systems.
By 2026, the challenge shifts from theoretical physics to systems engineering. Through milestones like Google Willow's advanced error correction and IBM's multi-chip Kookaburra processors, we are scaling toward thousands of complex operations. By leveraging industrial silicon manufacturing, we are finally achieving the high fidelities necessary for fault tolerance. We are no longer asking if this is possible. We've proven the underlying physics and are now simply building the stock to reach it.
To build a truly scalable quantum computer, we need more than just better hardware. We need a unified stack that bridges abstract mathematics and physical reality. In this NISQ era, success depends on deep hardware-software co-design, where error correction and fabrication techniques evolve together. By architecting this entire ecosystem, from high-level algorithms down to the control electronics, we can overcome environmental noise and finally translate theoretical quantities into practical real-world solutions.
While classical computing thrives on perfect abstraction, the NISQ era demands a different approach. Our current quantum hardware is noisy and resource-constrained, meaning rigid isolation between layers no longer works. We must move toward a model of continuous cross-layer co-design. By allowing physical constraints to permeate the entire stack, we can optimize algorithms and hardware in tandem. This transparency is vital. It's how we transform hardware limitations into actionable insights for more robust quantum computation.
Quantum computing demands a vertical approach to co-design. We can't just write software in a vacuum. We must bridge the gap between ideal algorithms and the constraints of noisy hardware. By integrating error correction with deep mathematical foundations, we wrap a fragile physical reality in robust theory. This holistic stack ensures every layer, from fabrication to compilation, works in unison. It's this deep integration that will ultimately turn theoretical quantum advantage into a practical, scalable reality.
Think of the quantum compiler as the ultimate bridge. It takes our pristine, high-level algorithms and translates them into the messy reality of physical hardware. While our initial designs assume perfect connectivity, real quantum devices have strict architectural constraints. The compiler must bend these algorithms, adding the routing and gate transformations necessary for them to actually run. Ultimately, we must sacrifice algorithmic purity for physical executability on today's noisy, imperfect hardware.
Bridging the gap between abstract logic and physical hardware requires a precise four-step mapping process. We begin by decomposing high-level algorithms into hardware-compatible primitives and scheduling operations to maximize efficiency. Next, we assign virtual qubits to physical locations and resolve connectivity constraints through intelligent routing. This transformation is essential for navigating hardware limitations, ensuring that our quantum programs are not just theoretically sound, but physically executable on today's complex and restricted quantum processors. It's crucial to understand that an algorithm's structure directly dictates the stress placed on quantum hardware. While random circuits feature complex, unstructured interactions that lead to a catastrophic overhead of swap gates, real-world algorithms like QAOA possess inherent patterns. This structural difference is vital. It allows compilers to exploit those patterns, significantly reducing routing demands and preserving the circuit fidelity needed for reliable computation as we scale up to more complex quantum gates. In the NISQ era, our hardware is inherently noisy, and increased circuit depth only amplifies these instabilities. To protect fragile quantum states, we rely on quantum error correcting codes. By utilizing entanglement and spatial redundancy, we distribute logical information across a larger subspace of physical qubits. This mathematical shield allows us to detect and correct errors without collapsing the underlying state, ensuring that our computations remain robust even in the face of inevitable hardware imperfections. Navigating the landscape of error correction requires moving from foundational baselines to adaptive frontiers. While stabilizer codes provide a robust classical starting point, mixed alphabet strategies allow us to optimize for heterogeneous hardware. We can further boost correctability through entanglement-assisted methods that leverage shared quantum resources. At the leading edge, spatiotemporal codes introduce dynamic, time-dependent models to combat noise. Together, these diverse strategies form a comprehensive toolkit for building truly resilient quantum systems. At the heart of every superconducting qubit is the Josephson junction, our nonlinear engine. Unlike a standard harmonic oscillator, this junction provides the critical anharmonicity needed to isolate a distinct two-level state. By facilitating Cooper pair tunneling, it creates a unique energy landscape where transition frequencies are well defined. Crucially, the junction's physical geometry directly shapes the circuit's Hamiltonian, allowing us to engineer the fundamental properties of the quantum bit with incredible precision. To scale up quantum device production, we must eliminate fabrication bottlenecks. Traditional Dolan-style junctions rely on fragile suspended bridges, leading to high variability and frequent mechanical failure. By transitioning to a Manhattan-style architecture, we overcome these structural weaknesses. This bridgeless approach uses overlapping perpendicular trenches, allowing the junction area to be defined purely by lithography. The result is a drastically more resilient process, with the high reproducibility required for advanced large-scale manufacturing. Precisely tuning the Hamiltonian is fundamental to quantum performance. By characterizing the oxidation dose, we've uncovered a predictable relationship between fabrication parameters and normal resistance. This allows us to target exact values with pinpoint accuracy, virtually eliminating the traditional trial and error approach to qubit frequency tuning. This deterministic control ensures we can scale our hardware reliably, moving from experimental guesswork to precise engineering, where every parameter is dictated by design. To truly understand how open systems evolve, we look to the GKSL generator. This mathematical framework captures the delicate balance between two competing forces: the internal, unitary evolution driven by the Hamiltonian and the irreversible dissipation caused by environmental coupling. By modeling this as a memory-less Markovian process, we can precisely quantify how quantum information decays over time. This foundational understanding is the essential bedrock required for designing robust systems and effective error correction. Think of the church of the larger Hilbert space as a fundamental lens for understanding quantum mechanics. Steinspring dilations prove that any noisy, dissipative system is actually just a subset of a perfectly unitary whole. When we zoom out far enough, chaos becomes order. However, this perspective comes with a catch. It necessitates an infinite dimensional environment and an unbounded Hamiltonian. To find that perfect mathematical purity, we must acknowledge the immense complexity surrounding every open system. We've reached a turning point where theoretical math, hardware fabrication, and compiler algorithms can no longer exist in silos. The future demands an open acceleration stack, a seamless integration of quantum processors and classical supercomputing. By embracing full-stack co-design and cross-layer optimization, we create a unified architecture that bridges the gap between abstract math and real-world results. This synthesis is how we finally make the impossible possible through total technological integration. To truly unlock quantum potential, we must first master its simulation. By harnessing the massive parallel power of thousands of classical GPU cores, we can precisely emulate, scale, and optimize complex quantum circuits. This high-performance environment provides a vital sandbox, allowing us to refine algorithms and error correction strategies long before they reach physical quantum hardware. We are essentially using the pinnacle of classical engineering to build the essential foundation for the quantum era. At its core, quantum mechanics translates directly into massive linear algebra. This means you don't need a quantum processor to execute these algorithms today. A quantum state is ultimately a vast array of complex numbers, and applying a gate is simply performing high-speed matrix multiplication. Because classical GPUs were fundamentally designed for these exact operations, we can simulate complex quantum behaviors with incredible efficiency. This allows us to bridge the gap between theory and reality using current hardware.
Quantum simulation depends on massive parallel operations that quickly overwhelm traditional CPUs. We reach a critical tipping point at 16 qubits, where GPUs begin to significantly outperform multi-core processors. As qubit counts scale, the advantage becomes exponential, achieving nearly 150 times speedup. This massive performance gain, driven by thousands of SIMT cores, allows us to practically emulate intermediate-scale quantum algorithms today, bridging the gap long before large-scale quantum hardware is fully available.
When simulating quantum systems on classical hardware, we face a brutal physical wall: memory. To track an exact state vector, every additional qubit doubles the required VRAM. This isn't a processing speed bottleneck, it's a fundamental capacity explosion. While 20 qubits require a mere 16 megabytes, scaling to just 40 qubits demands a staggering 16 terabytes. This exponential growth quickly shatters the limits of modern silicon, making large-scale classical emulation physically impossible.
Translating hardware specs into quantum capacity requires understanding exponential memory growth. At 30 qubits, simulation demands roughly 16 gigabytes of VRAM. This is a strict threshold. For instance, pushing a 40 gigabyte A100 past 32 qubits triggers an immediate fatal error. Whether you're using an L4 for efficiency or an 8-way cluster for 36 qubits, your hardware choice must match your qubit target. Respecting these ceilings is critical to preventing crashes and ensuring simulation stability across your infrastructure.
Let's explore our first paradigm, state vector simulation, or SVS. Think of this as the brute force approach. It tracks the complete wave function of a closed system, providing an exact mathematical representation. This makes SVS the gold standard for deep, highly entangled circuits. But remember, we face a hard physical cap at roughly 35 qubits. Your bottleneck isn't compute density, it's entirely bound by your available memory bandwidth and throughput. Next, let's explore tensor network simulation. This paradigm bypasses the exponential memory bottleneck of state vectors by reformulating quantum circuits as networks of local tensors. By finding efficient paths to contract these networks, we can simulate thousands of qubits on a single GPU. It's incredibly powerful for shallow or low entanglement circuits. However, as entanglement increases, the required bond dimension causes computation time to saturate, making pathfinding a massive NP-hard challenge. To maximize efficiency, we must intelligently route workloads based on circuit complexity. For high entanglement tasks under 35 qubits, state vector simulation is our go-to, despite VRAM limits. When scaling over 100 qubits, we shift to tensor networks, which thrive on structured, low entanglement profiles. Finally, for modeling environmental noise, density matrix simulation is essential, though extreme memory scaling restricts qubit counts. Selecting the right engine ensures peak performance without hitting architectural bottlenecks. To truly unlock quantum potential, we need a robust software stack that bridges complex algorithms with powerful silicon. It starts at the application layer with solvers like VQE, passing through established frameworks like Qiskit. The core efficiency comes as high-level libraries automatically filter these commands into optimized tensor operations. These are then accelerated by backends like cuQuantum and executed directly on advanced SIMT hardware, ensuring maximum performance for today's quantum computing tasks. Selecting the right Python front-end is essential for quantum development. Qiskit remains the industry standard, offering robust support and seamless back-end integration. If your focus is machine learning, PennyLane's differential programming is indispensable. For hardware-level optimization, Cirq provides unmatched precision and Sycamore parity. Finally, Kibo acts as a modular bridge, allowing zero-code transitions from GPU simulation to physical hardware. Your choice depends on whether you prioritize community support, machine learning integration, or fine-grained hardware control.
To maximize performance, we must address the VRAM bottleneck. By utilizing directed acyclic graphs, our simulators scan the circuit to fuse multiple small gates into a single optimized multi-qubit operation. This drastically cuts down on expensive data transfers, reducing read-writes by up to 75%. We validated this approach on IBM's Heron-class QPU, where a 42-gate circuit was compressed into just 14 operations, proving that smarter compilation is key to scaling quantum simulation.
Simulating 36 qubits requires a staggering 640 gigabytes of memory, forcing us to fragment the state vector across an 8-unit A100 cluster. Standard connections simply can't handle the massive data exchange needed when gates act on split qubits. By utilizing ultra-high-speed NVLink interconnects at 600 gigabytes per second, we overcome these hardware bottlenecks. This architecture delivers an incredible 90 times speedup over traditional CPU setups, making large-scale quantum simulations finally feasible.
To ensure system stability during intensive computations, we've implemented a memory-aware CPU fallback mechanism. When the dynamic monitor detects that a task will exceed available VRAM, it triggers a failsafe to prevent a fatal crash. The system automatically pauses and offloads the state vector to host RAM via the PCIe bus. Once the CPU processes the data, it migrates back to the GPU, ensuring seamless execution even under extreme memory pressure.
In the NISQ era, real-world quantum hardware is inherently noisy. To design effective error correction, we must accurately simulate how qubits interact with environmental noise and thermal fluctuations using the density matrix. This is where QDensityMat changes the game. By mapping open systems via tensor product contractions, we've achieved a staggering 186 speedup over traditional CPU runs. This performance leap allows us to simulate the messy reality of quantum systems with unprecedented speed and precision.
Your classical GPU is the fundamental bridge required to master the post-quantum era. Currently, these processors drive two critical fronts. They allow us to simulate complex qubit environments to design the fault-tolerant hardware of tomorrow. Simultaneously, they power the implementation of NIST's latest cryptographic standards, protecting today's data from future harvest now, decrypt later threats. By leveraging this classical power, we are not just preparing for the quantum future, we are actively building and securing it.
The post-quantum cryptography imperative is no longer a distant concern. It is a strategic necessity. With the August 2024 NIST FIPS standards now finalized, we have the definitive framework to secure our infrastructure against quantum threats. Our roadmap focuses on three critical phases: discovery, algorithmic transition, and full enterprise deployment. By implementing these quantum-resistant fortifications today, we ensure our digital assets remain protected against the next generation of cryptographic challenges. Let's explore the playbook. Think quantum computing is a future problem? Think again. The breach is happening right now. Through harvest now, decrypt later attacks, adversaries are stealing your encrypted data today, simply waiting for Q-Day to unlock it. This means any information with a long shelf life, from intellectual property to classified communications, is already compromised if secured by legacy algorithms. We cannot wait for the hardware to arrive. We must address this threat immediately. Quantum computing introduces two critical vulnerabilities that redefine modern security. Shor's algorithm provides an exponential speedup that fundamentally breaks public key cryptography, rendering RSA and ECC obsolete. Simultaneously, Grover's algorithm delivers a quadratic speedup that weakens symmetric encryption, effectively halving the bit strength of our current standards.
To defend against this quantum threat engine, we must transition to entirely new mathematical foundations and double our key sizes to ensure our data remains secure in the post-quantum era.
We have reached a critical turning point in digital security. With the recent NIST standardization, we are witnessing a fundamental paradigm shift. We're moving beyond traditional prime factorization toward new mathematical frontiers like structured lattices. These complex problems are computationally infeasible for both classical and quantum systems. To ensure absolute resilience, we're also integrating hash and code-based fallbacks as vital insurance. This mathematical shield secures our most sensitive data against the quantum threats of tomorrow. Let's explore the primary tools in our PQC's standard arsenal. MLChem and MLDSA serve as the lattice-based backbone for key exchange and digital signatures, securing everything from TLS to identity management. To ensure long-term security, SLH-DSA provides a robust hash-based fallback. Finally, we're anticipating HQC's selection in 2025 to add crucial mathematical diversity. Together, these standards provide a multi-layered defense, ensuring our digital infrastructure remains secure in a post-quantum world.
Transitioning to post-quantum cryptography is a massive architectural shift, not just a simple software patch. We're moving from lightweight legacy keys to heavy PQC algorithms, where key and signature sizes are exploding, often over 30 times larger than current standards. This creates immediate infrastructure restriction, leading to network fragmentation and increased latency. To manage these intense computational demands, we must evolve our hardware, utilizing specialized acceleration to ensure security doesn't come at the cost of performance.
We are facing a dangerous timeline collision. While quantum hardware is accelerating, with breakthroughs drastically reducing the requirements to break encryption, enterprise migration still takes up to a decade. This squeeze has collapsed our safety margin by 95%. Based on historical transitions, organizations waiting for a fault-tolerant quantum computer to emerge before they begin migrating will be breached. We can no longer afford to wait. The window for a secure transition is closing today.
We're entering a period of global regulatory squeeze. From the US to Europe and Australia, governments are mandating a rapid shift toward post-quantum readiness with firm deadlines between 2030 and 2035. However, the most immediate challenge is the September 2026 FIPS 140.2 sunset. This transition to FIPS 140.3 will create a massive procurement bottleneck and a significant validation backlog. To maintain compliance and market access, we must begin our migration before the window closes.
As we navigate the shift toward a quantum-resistant future, hybrid cryptography serves as our vital transition bridge. By weaving classical algorithms together with new post-quantum methods in a single handshake, we create a crucial fail-safe. Your data remains secure as long as at least one underlying algorithm stays unbroken. While global policies differ on specific implementations, this dual-layered approach provides the necessary resilience to protect our digital infrastructure against both current threats and the coming quantum era.
The post-quantum cryptography ecosystem is maturing across three critical fronts. First, pure-play innovators like Sandbox AQ provide foundational security libraries. Next, hyperscalers like Google and AWS are integrating MLChem standards at scale, with 2029 migration deadlines looming. Finally, hardware specialists are layering in physical entropy through quantum key distribution for ultra-high assurance environments. Together, these sectors are building a robust, multi-layered defense to secure our digital future against quantum threats.
In our push toward cryptographic migration, the biggest hurdle isn't the mathematics, it's visibility. You simply cannot secure what you haven't mapped. This cryptographic blind spot is now a legal and financial liability, as federal mandates and insurance underwriters now demand a comprehensive inventory. To remain compliant and secure, your automated discovery must penetrate deep into TLS terminators, application code, and embedded firmware. We must move from uncertainty to a fully visible, defensible infrastructure.
In the quantum era,
Rigid, hard-coded cryptography is no longer just a limitation, it's a terminal risk. If an algorithm is compromised, your entire security posture collapses. That's why crypto agility is our strategic imperative. It's the architectural capability to swap out cryptographic components instantly, without rewriting core logic or suffering downtime. By building this modular flexibility today, we future-proof our infrastructure, ensuring we can pivot to new standards the moment a vulnerability is discovered. To secure our enterprise against future quantum threats, we must follow a structured playbook. We start by inventorying all public key dependencies and prioritizing assets vulnerable to harvest now, decrypt later risks. By re-architecting for cryptographic agility and testing hybrid models, we ensure a seamless transition without disrupting operations. This phased rollout allows us to sunset legacy standards ahead of the 2035 deadlines, maintaining long-term data integrity in an increasingly complex post-quantum world. To navigate the quantum threat, we use this scorecard as our strategic compass. First, we need total visibility. Can we generate a complete cryptographic bill of materials right now? Next, we must assess exposure by identifying data whose shelf life extends beyond 2033. We also need to hold our supply chain accountable for FIPS-validated post-quantum standards like ML-Chem. Finally, quantum readiness requires a multi-year budget aligned with 2030 TLS deprecation timelines. It's time to benchmark our progress.
The quantum era is no longer a distant hypothesis. It's an immediate engineering challenge with clear milestones and enforceable deadlines. Our mandate is urgent. We must execute crypto agile migrations today to safeguard our data against future retroactive decryption. Organizations that delay this transition risk catastrophic exposure and unsustainable crisis spending. By acting now, we can secure our digital infrastructure and ensure our most sensitive information remains protected in the post-quantum landscape. To truly harness quantum power, we must look beyond individual components and master the entire simulation landscape. This ecosystem represents a strategic convergence where mathematical models, sophisticated software, and physical hardware interlock. By mapping these modalities, we identified the most efficient pathways for discovery. Our focus is moving from theoretical potential to practical outcomes, ensuring every layer of the quantum stack works in harmony to solve the complex challenges that classical systems simply cannot touch.
We currently operate in the NISQ era, where hardware limitations like high error rates and restricted circuit depth remain significant hurdles. To navigate this, robust classical simulation serves as our mandatory bridge. It provides a noise-free environment for perfect state extraction and exact algorithm validation, free from hardware cues. By mastering our algorithms through simulation today, we are building the necessary foundation to transition successfully into the future of fault-tolerant quantum computing.
Think of differentiable quantum programming as a high-speed feedback loop. We use advanced simulators to evaluate circuits, feeding that data into a classical optimizer to update parameters. The key innovation here is adjoint differentiation. By calculating gradients directly during backpropagation, we eliminate the need for repetitive circuit runs. This breakthrough reduces total evaluations by up to 90%, allowing us to train sophisticated quantum models with unprecedented speed and efficiency.
Choosing the right simulation method is critical for balancing computational cost with physical accuracy. State vector simulation offers exact amplitude tracking, providing the ultimate ground truth for smaller circuits. When we scale up, tensor networks allow us to handle higher qubit counts by efficiently compressing entanglement. Finally, for modeling real-world hardware, density matrix simulations are indispensable, offering comprehensive noise modeling for open systems. Together, these three methodologies provide a complete toolkit for quantum verification.
Classical hardware faces a fundamental bottleneck, the memory wall. Because state vector simulations require exponential memory growth, the demand for RAM quickly becomes insurmountable. While 24 qubits require mere megabytes, reaching 50 qubits pushes us to the exascale limit of 16,000 terabytes.
At this scale, unavoidable cache saturation and memory bandwidth limits create a hard ceiling. This exponential explosion proves why classical computers ultimately cannot keep pace with the massive scale of quantum complexity. Simulating quantum circuits involves transforming gates into a complex tensor network. The critical stage is contraction, where we encounter the entanglement bottleneck. With low entanglement, networks remain manageable, allowing us to simulate hundreds of qubits with ease. But as entanglement increases, bond dimensions grow exponentially. Finding an efficient contraction path becomes an NP hard challenge, causing memory requirements to explode. Understanding this limit is vital for optimizing our classical simulations of quantum systems. When we transition from ideal quantum systems to real-world noisy environments, the computational cost skyrockets. Modeling noise requires tracking classical uncertainty through the density matrix, rather than simple state vectors. This shift squares our memory requirements, moving from 2 to the n to 2 to the 2n parameters. Consequently, simulating these complex mixed states on standard cloud infrastructure is strictly capped at roughly 17 qubits. This overhead remains a massive hurdle for large-scale, high-fidelity quantum simulations.
Choosing the right simulation method is a balance between computational complexity and the physical insights you need. For high-fidelity, deeply entangled circuits, state vectors are the gold standard despite their exponential memory requirements. In contrast, tensor networks excel at simulating shallow, local circuits more efficiently. If you're modeling environmental noise, density matrices are essential, while stabilizer simulators offer the unique ability to scale to massive qubit counts, making them perfect for testing quantum error correction protocols.
Imagine writing a single Python script that runs optimally across any hardware environment. Whether you're building in Qiskit or PennyLane, your code is transparently routed to high-performance C++ and CUDA execution engines. This architecture automatically scales your workloads from local GPUs to massive cloud and exascale systems. By abstracting the underlying hardware, we empower you to achieve maximum performance without rewriting your code. It's the ultimate combination of developer simplicity and raw power. Navigating the quantum software landscape requires choosing the right tool for your specific objective. Qiskit serves as our industry standard, offering deep IBM integration and robust circuit transpilation. For researchers bridging quantum and machine learning, PennyLane provides essential differentiable programming. Meanwhile, Cirq offers the hardware-aware precision needed for Google's Sycamore processor through explicit gate timing control. Finally, Kibo provides a modular end-to-end solution that turns them seamlessly from high-level simulation to physical FPGA pulse control. NVIDIA Q-Quantum is a game-changer for quantum circuit simulations. By leveraging QStateVec on multi-node GPU clusters, we achieve massive speedups, ranging from 64x to an incredible 146x over traditional CPU baselines. Our optimized memory management maintains high efficiency across both H100 and A100 architectures, even for deep circuits. Most importantly, this power integrates invisibly into your existing Python SDKs, requiring zero user compilation. It's about delivering world-class performance without complicating your development workflow. Traditionally, legacy systems struggle with network latency during every iteration, creating a significant bottleneck. By transitioning to embedded simulation, we consolidate the algorithm code and the GPU simulator into a single unified container. This shift eliminates round-trip delays entirely, enabling instant iteration. The impact is transformative. Complex hybrid variational algorithms that once required hours to run are now completed in just minutes. This leap in architectural efficiency significantly accelerates our development and discovery timelines. To understand the power of our engine, let's look under the hood. We utilize 3 core operations for peak efficiency. Gate fusion minimizes memory overhead by combining complex cubic sequences into single operations. Adaptive precision then dynamically scales numerical fidelity based on real-time demands, balancing speed and accuracy. Finally, our memory fallback safeguard prevents system crashes by automatically routing overflow data from the GPU to system RAM.
Together, these features ensure a seamless, high-performance simulation experience.
When selecting a quantum simulation engine, your workload's specific requirements dictate the optimal approach. If environmental noise is critical, density matrix simulators are necessary, albeit limited in scale. For massive Clifford-only circuits, stabilizer simulators can efficiently handle millions of qubits. General, highly entangled circuits typically require state vector methods, which hit a memory wall around 50 qubits. Finally, for shallow circuits with local connectivity, tensor networks offer a powerful path to simulate hundreds of qubits. Simulation serves as the vital scaffold for quantum utility. By leveraging classical simulators, we define the precise boundaries where quantum advantage begins. These simulations are mandatory for architecting the fault-tolerant error correction codes our hardware depends on. Ultimately, the future of high-performance computing is inherently hybrid. We are entering an era where exascale hardware and QPUs operate in tandem, merging classical strength with quantum potential to solve the world's most complex challenges.
Let's explore the architectural bridge between quantum theory and classical execution. To simulate the NISQ era, we must represent complex quantum states through high-dimensional tensor networks. The real challenge lies in the mapping and optimization layer, which translates these abstract mathematical contractions into physical data flows. By feeding these optimized workloads into massive parallel processing units with high bandwidth memory, we can effectively emulate quantum behavior on classical silicon, pushing the boundaries of what's possible today.
Right now, we are in a transition period where physical quantum hardware remains constrained by noise and limited scale. This is why classical emulation is so vital. While current QPUs grapple with high error rates and probabilistic noise, simulators provide a noise-free ground truth. They allow us to access full state vectors and validate algorithms with absolute precision. Until fault-tolerant systems arrive, classical simulation remains our most essential tool for development and hardware co-design.
To build a quantum simulator, we must map the exponential complexity of quantum mechanics onto classical silicon. Our journey begins with selecting a robust mathematical engine. We then leverage GPU-accelerated hardware to handle the heavy computational load. Software-level gate fusion and compilation further optimize this process. By scaling across distributed cloud architectures, we achieve the performance needed for hybrid jobs. Finally, rigorous benchmarking ensures our results align with ground truth, turning complex theory into a reliable, scalable reality.
State vector simulators provide mathematical perfection by tracking the complete wave function, but they face a daunting challenge: the exponential memory explosion. Since requirements double with every added qubit, we quickly hit a physical wall. While 32 qubits might fit on a high-end server, 50 qubits demand over 10 petabytes of RAM, far surpassing the limits of modern hardware. This exponential growth is the fundamental bottleneck that makes classical simulation of large-scale quantum systems practically impossible.
Traditional state vector methods hit a memory wall because they treat data as one rigid, unbreakable block. This restricts our simulations to a very small number of qubits. To break through, we transition to tensor networks. By representing circuits as a flexible web of tensors, we can use SVD truncation to prune low entanglement connections. This modular approach bypasses previous memory constraints, allowing us to scale to hundreds of qubits for complex quantum algorithms.
Selecting the right simulation engine depends on your specific algorithmic goals. For exact validation of deep entangled circuits, state vectors are the gold standard. If you're tackling large-scale but shallow circuits, tensor networks offer the necessary efficiency. When physical noise and decoherence are critical, the density matrix approach provides essential real-world calibration. Finally, for massive fault tolerance design and error correction involving millions of qubits, the stabilized method is your best choice for extreme scale.
To simulate quantum states, we must apply gate matrices across exponential arrays. Traditional CPUs struggle here, hitting a severe serial processing bottleneck because they can only handle so much data sequentially. The real breakthrough comes when we shift to GPU architectures. By leveraging thousands of SIMT cores, we bypass those memory latencies entirely. This transforms a crushing computational bottleneck into a massively parallel workload, unlocking the high throughput required for complex state vector simulations.
Next, let's discuss how we accelerate these simulations using NVIDIA cuQuantum. This specialized SDK bypasses standard linear algebra constraints by utilizing bespoke, low-level primitives designed for quantum circuits. With the QState VEC engine, we achieve a 30-fold speedup over traditional CPU simulators on a single A100. For more complex parallel workloads, the QTensorNet engine delivers staggering gains of up to 90 times. Together, they unlock unprecedented performance on our DGX nodes, pushing the boundaries of quantum research.
In this stage, we bridge the gap between abstract logic and physical hardware. You don't need to write raw matrix multiplications. Instead, frameworks like Qiskit or PennyLane act as your primary interface. Your high-level code is compiled into an intermediate representation, optimizing and routing instructions automatically. Finally, these operations are lowered to specific execution backends, from simulators to GPU-accelerated clusters. This abstraction layer ensures that your quantum programs remain portable, hardware-agnostic, and ready for scale.
Now, let's look at the gate fusion engine. To maximize efficiency, our compiler pre-calculates the mathematical results of entire gate sequences before they ever hit the hardware. Instead of the GPU struggling with repeated, costly memory fetches for every individual gate, it simply executes one single fused unitary matrix. This transformation reduces 6 separate memory operations down to just one, drastically cutting down overhead and unlocking a massive boost in simulation speed on the GPU.
Let's address the core challenge, the hybrid bottleneck. In variational algorithms, classical optimizers must iteratively tune quantum parameters. However, we're hitting an insurmountable latency wall. Requiring over 100,000 sequential circuit executions per epoch means local processing times can skyrocket from hours to weeks. This massive delay in the feedback loop stalls progress, making it the primary hurdle we need to clear to unlock the true potential of these iterative quantum systems.
To achieve true scale, we've embedded our simulators directly within the same cloud containers hosting your application code. This eliminates round-trip latency, allowing your quantum workloads to scale out seamlessly across distributed fleets. By bypassing local memory limits and running tasks in parallel, you gain predictable performance and high-fidelity noise modeling. This architecture ensures your most complex algorithms transition effortlessly from local development to massive, high-speed cloud execution, removing the bottlenecks of traditional simulation.
In Step 5, we establish confidence through ground truth benchmarking. Before trusting any simulation, we must verify mathematical precision against known analytical targets. By using primitives like the quantum Fourier transform, we can cross-validate engines including ERA and QSIM. The results show negligible error deviation, maintaining full double precision accuracy throughout. This level of consistency confirms our system's logical integrity, ensuring that our foundational calculations are flawless before we tackle more advanced quantum architectures.
This is our complete full-stack simulator architecture, a powerful bridge between abstract quantum logic and high-performance hardware. By integrating industry-standard frameworks like Qiskit and PennyLane with NVIDIA cuQuantum, we harness the massive scale of GPU supercomputing. This seamless pipeline transforms high-level algorithms into optimized executions, allowing you to simulate complex quantum workflows with unprecedented speed. It provides a robust, scalable foundation for developing the quantum future using today's most advanced classical infrastructure.
Scaling quantum computing requires moving beyond bespoke lab experiments toward industrial-grade systems engineering. This means mastering two critical frontiers: sub-10 nanometer atomic lithography for high-density silicon arrays, and the extreme cryogenics needed to reach temperatures near absolute zero.
By synchronizing this chandelier infrastructure with high-yield manufacturing, we are turning a scientific breakthrough into a scalable reality. This is the industrialization of the quantum blueprint, bridging the gap between quantum theory and reliable, world-changing technology. Navigating the quantum landscape requires understanding the fundamental trade-offs between different modalities. While superconducting and silicon systems offer rapid gate speeds, they often battle shorter coherence or manufacturing precision. In contrast, trapped ions in neutral atoms excel in stability, maintaining coherence for seconds or more, but at the cost of speed. Photonic systems promise ballistic performance, but face significant loss challenges. Ultimately, every approach encounters a unique physical bottleneck that defines the current engineering frontier of the industry.
Moving past the traditional Dolan bridge technique is essential for scaling superconducting circuits. While legacy double angle evaporation suffers from fragility and inconsistent critical currents, the Manhattan-style transition significantly improves reproducibility through lithographic precision. However, the true leap forward is the scalable window junction. By utilizing an SiO2 scaffold and vapor etching to eliminate residue, we drastically mitigate TLS defects. This advancement achieves impressive relaxation times of 57 microseconds, providing a robust foundation for next-generation quantum processors.
To scale quantum computing, we must leverage the global CMOS foundry infrastructure. This transition hinges on two breakthroughs. First, we replace natural silicon with isotopically purified silicon-28, creating a pristine semiconductor vacuum free from magnetic noise. Second, we push past lithographic limits. By employing high-NA EUV lithography, we achieve 6-nanometer precision to confine single electrons reliably. This synergy ensures over 99% fidelity across entire wafers, turning theoretical quantum advantage into industrial reality.
We're revolutionizing quantum networking with photonic integrated quantum circuits. By using bi-fi diaryl carbene molecules, we achieve atomic precision through organic synthesis, avoiding the randomness of traditional defects. Integrating these molecules onto TFLN circuits provides millisecond coherence and an ideal qubit-photon interface. Crucially, our hybrid architecture utilizes Flow-K codes to tolerate up to 70% photon loss. This synergy of molecular control and robust fault tolerance marks a major leap towards scalable, real-world quantum systems. Maintaining a stable quantum state requires extreme cryogenic cooling down to the millikelvin range. This journey begins with mechanical pulse tubes and ends in the mixing chamber, where helium-3 phase crossing creates the core operational zone. Crucially, as we scale toward 500-plus qubits, cooling demands skyrocket. Investing in these systems is a major strategic decision. Production-tier refrigerators represent a multi-million-dollar commitment, but they are the necessary foundation for high-capacity, fault-tolerant quantum computing. Moving quantum computing into real-world data centers requires a radical shift in hardware. While superconducting systems demand massive cryogenic cooling and reinforced flooring, neutral atom packaging offers a streamlined alternative. It fits within a standard 19-inch rack and operates at room temperature, drawing minimal power. Although managing the complex laser arrays remains a challenge, eliminating the need for heavy liquid helium infrastructure is a game changer. This approach finally makes quantum integration both practical and scalable.
To manage this quantum processor, we utilize an integrated optical nervous system. First, 1064-nanometer lasers act as optical tweezers, cooling neutral atoms to near absolute zero. Once stabilized, precise 297-nanometer UV pulses drive Rydberg excitations to execute the high-fidelity entangling gates required for computation. Finally, real-time wavefront sensors continuously correct sub-nanometer aberrations. This orchestration maintains the perfect stability and precision needed to ensure our quantum operations remain reliable and error-free. To scale quantum processors, we must overcome the coaxial bottleneck. Current superconducting systems require over 200 signal lines for just 100 qubits, creating a dense microwave nervous system. This isn't just a spatial challenge. every wire acts as a thermal bridge that can disrupt fragile quantum states. By transitioning to silicon spin qubits, we can utilize DC gate lines instead. This drastically reduces the heat load, enabling larger-scale processors to run in far more efficient cryostats.
Scaling ion traps requires overcoming the linear trap limit, where overcrowding ions causes decoherence. Our solution is the QCCD architecture. By physically shuttling ions through microfabricated junctions into small capacity zones, we achieve high-fidelity gates without the heating issues of larger chains. This mobility adds complexity. Therefore, our compilers must strategically map circuits to the hardware spatial graph. This minimizes transit distances, ensuring peak performance and stability as we continue to scale our quantum processors.
To achieve true quantum advantage, we must bridge the gap between classical and quantum systems with near-zero latency. Our orchestration stack integrates high-performance classical accelerators with the QPU through a dedicated pulse processing unit. This bypasses traditional network delays, enabling microsecond latency feedback loops for AI-driven calibration. By overcoming this speed limit, we can perform complex error correction and dynamic pulse synthesis in real time, maintaining coherence before these fragile quantum states dephase.
While quantum physics gets the headlines, the real battle is won in the supply chain. To scale, we must secure rare materials like enriched silicon-28 and helium-3, which are in critically short supply. Furthermore, the industry faces severe bottlenecks in foundry access and specialized cryogenics, where lead times can exceed a year. Overcoming these hidden material and infrastructure gaps is the only way to move from lab prototypes to industrial-grade quantum systems. To build a viable quantum computer, we must achieve total integrated mastery across vastly different disciplines. We're moving beyond isolated components to a full-stack synthesis. This architecture bridges classical orchestration with high-precision fabrication, linked by a complex nervous system of connectivity. In this environment, every nanometer of surface roughness and every microsecond of latency matters. Our ultimate goal is to translate fragile, probabilistic quantum states into robust, industrial-scale computational infrastructure that delivers deterministic results.
We have reached a defining inflection point. The industry has exited the era of heroic physics experiments. Today, winning the quantum race requires more than just world-class physicists. It demands mastering the unyielding realities of global supply chains, precision nanofabrication, and full-stack systems engineering. As we transition from laboratory demonstrations towards foundry-scale integration, success will be claimed by those who can bridge the gap between theoretical breakthroughs and industrial-scale manufacturing excellence. Welcome, everyone. Today, we're bridging the gap between subatomic physics and the reality of full-stack quantum architecture. To master quantum computing, we must look beyond individual qubits and see how operations like Hadamard transforms and CNOT gates orchestrate entanglement. Maintaining high fidelity and coherence is the ultimate engineering challenge. Our goal is to harness these fragile states into a stable, scalable system that fundamentally redefines how we process information and solve complex problems.
To understand quantum computing, we must recognize the fundamental shift from bits to qubits. Traditional bits are deterministic, like a coin that is strictly heads or tails, and process information sequentially. Qubits, however, leverage probabilistic mechanics. Through superposition, they can represent multiple states simultaneously. While two classical bits evaluate only one state at a time, two qubits evaluate 4 states at once. This represents a dimensional expansion of computation, unlocking power that classical systems simply cannot achieve.
To truly unlock the power of quantum computing, we must understand its 3 fundamental pillars. First, superposition allows qubits to exist in multiple states simultaneously, enabling immense parallel processing. Next, entanglement mathematically links these qubits, so the state of one instantly defines the other, allowing the system to scale exponentially. Finally, interference lets us manipulate these probabilities, amplifying correct answers while canceling out incorrect paths. Together, they represent a revolutionary shift in how we compute.
In the logic layer, we orchestrate the transformation of quantum information. We start by initializing qubits into a clean ground state. Then we manipulate them using gates. The Hadamard gate creates superposition, while the CNOT gate entangles qubits, linking their states together. This precise choreography allows for massive parallel computations. Finally, measurement collapses the wave function, translating these quantum states back into the classical binary data we can ultimately use.
Building a quantum computer is a constant battle against decoherence. Qubits are exceptionally fragile. Even the slightest heat or vibration causes their quantum state to collapse. We track this through T1 and T2 times, which represent the ticking clock for any computation. Our biggest engineering hurdle is creating an environment that perfectly isolates these delicate systems from noise, while still allowing us to manipulate and control them. Without stability, the promise of quantum power remains out of reach.
The race for the perfect qubit is far from over, as no single modality currently excels in every category. It's a landscape defined by critical trade-offs. Superconducting circuits and silicon spins deliver blistering gate speeds, but face extreme environmental challenges. Meanwhile, trapped ions and neutral atoms offer exceptional coherence at the cost of speed. Each path represents a different technological gamble on how we'll achieve scale. There is no best hardware, only the right balance for the future.
In the quantum world, we face a fundamental tug-of-war between speed and stability. On one end, superconducting qubits offer lightning-fast gate speeds, but decay in mere microseconds. On the other, trapped ions and bosonic cat qubits provide incredible stability, lasting minutes or even hours, though they operate much slower. As we look across this spectrum, it's clear there's no universal winner yet. Success depends on balancing rapid execution against the precious gift of coherence duration.
Moving to the software layer, we distinguish between our current capabilities and our future potential. Today, in the NISQ era, hybrid algorithms like VQE and QAOA allow us to navigate hardware noise for breakthroughs in chemistry and logistics. Looking ahead, we're building toward fault-tolerant quantum computing. Once full error correction is realized, powerhouse algorithms like Shor's and Grover's will fundamentally redefine cryptography and search. This evolution marks the transition from experimental utility to transformational, industry-wide impact. Quantum computing isn't a replacement for classical systems, it's their ultimate evolution. In this quantum-centric architecture, classical nodes act as orchestrators, managing complex logic and optimization. Meanwhile, the QPU serves as a specialized accelerator, tackling specific, intractable math kernels. Connected by a low-latency bridge, these systems work in tandem to solve once-impossible problems. Much like the GPU revolutionized AI, this hybrid synergy is the key to unlocking the next generation of supercomputing performance. Quantum simulators are essential for developing tomorrow's algorithms, but they face a brutal reality: exponential memory growth. A laptop can simulate 30 qubits, yet 40 qubits requires a full supercomputer cluster. By 50, we need an exascale machine with 16 petabytes of RAM. To push past this limit and explore 50-plus qubits, we rely on cloud-scale infrastructure and GPU acceleration. It's a brute force challenge that serves as our vital testing ground for the quantum era. Selecting the ideal quantum simulator depends entirely on your project's constraints. For deep, highly entangled circuits needing exact precision, state vector simulators are the gold standard. If you're pushing toward massive qubit counts with low entanglement, tensor networks offer a clever way to bypass memory limits. Finally, for researchers studying the impact of hardware noise and decoherence, density matrix simulators are essential to capture real-world environmental errors. Let's find the perfect tool for your specific workload. Quantum compilation is the essential bridge between abstract algorithms and physical hardware. We begin with high-level code, which must be transpiled into a device's native instruction set.
From there, we navigate the chip's rigid connectivity through precise routing before finally converting operations into analog control pulses. Remember, every gate counts. A smart compiler optimizes these steps to shorten circuits, allowing us to execute faster and beat the ever-ticking decoherence clock.
Quantum computing is fundamentally redefining how we tackle humanity's most complex challenges. By simulating molecular interactions at a subatomic level, we're accelerating the discovery of life-saving drugs and revolutionary materials. In industry, quantum algorithms navigate massive datasets to optimize global supply chains and financial portfolios. While these capabilities challenge traditional encryption, they also drive an essential transition toward post-quantum security. This technology represents a paradigm shift, unlocking solutions that were previously beyond our reach.
Achieving practical quantum utility requires far more than just increasing qubit counts. We must orchestrate a seamless synergy across the entire stack. This means integrating breakthroughs in physical hardware and control systems with sophisticated execution layers and real-world applications. Success isn't found in a single component. It's found in the simultaneous evolution of every layer. Only through this unified, integrated approach can we bridge the gap between experimental physics and transformative real-world solutions.
We are currently crossing a monumental threshold. For years, quantum computing was largely a theoretical dream, but today we are entering the era of quantum utility. This shift is powered by hardware that is finally scaling and error correction that is rapidly advancing. With our hybrid software ecosystem now ready, the transition is underway. This revolution won't arrive all at once. It's being built piece by piece, one physical qubit, one logical gate, and one optimized algorithm at a time. Let's explore the incredible architecture of absolute zero. Quantum computing requires an environment colder than deep space to maintain the stability of fragile qubits. We're moving from the physical hardware of dilution refrigerators to the sophisticated cloud simulators that bring this power to your fingertips. This integrated stack represents a massive leap in engineering, connecting quantum mechanical phenomena with high-level computation to solve the world's most complex challenges. Are you ready to dive in? Let's explore the striking scale discrepancy we call the quantum paradox. At its heart, the actual computing chip is microscopic, featuring components just 100 nanometers wide. Yet, to make it work, we must surround it with a massive shell. In fact, 99% of the physical machine is a sophisticated life support system, providing extreme cryogenics, shielding, and control wiring. We are essentially building massive, complex environments just to harness the power of the microscopic.
At the heart of this technology is the qubit. Unlike traditional bits that are strictly 0 or 1, qubits leverage superposition to process vast data sets in parallel. Through entanglement, these qubits share information instantly to execute complex logic. We bring this to life using superconducting circuits and Josephson junctions, where precise microwave pulses manipulate these fragile quantum states to unlock computational power previously thought impossible.
As we engineer the quantum future, 4 distinct paths have emerged, each with unique trade-offs. Superconducting qubits offer incredible speed, but demand extreme cooling. Silicon spin leverages existing chip manufacturing infrastructure for better stability. Neutral atoms provide superior coherence, staying stable for seconds in room temperature vacuums. Meanwhile, photonic systems use light to bypass cooling requirements entirely. Understanding these modalities is crucial, as the winner will likely be defined by how effectively we balance speed, stability, and scalability.
Quantum states are incredibly delicate, and their greatest enemy is heat. Think of heat as chaotic atomic vibration. When thermal energy interacts with a qubit, it disrupts its coherence, turning a stable wave into random noise. This process, decoherence, destroys our calculations before they can even finish.
To solve this, we must achieve temperatures colder than deep space, freezing out ambient energy to ensure our quantum processors can perform with the absolute precision required. To harness quantum power, we must reach temperatures colder than deep space. This dilution refrigerator achieves that through a sophisticated three-stage process. First, a pulse tube pre-cools the system using compressed helium. Next, the still drives circulation through vacuum distillation. Finally, we reach the mixing chamber, plunging to 10 millikelvin. This is the heart of the machine, creating the ultra-cold environment where our quantum processor resides. It's an expensive but vital feat of engineering. To reach absolute zero, we leverage the fascinating physics of helium isotopes. Below 0.87 Kelvin, helium-3 and helium-4 separate into distinct liquid phases. To maintain equilibrium, helium-3 atoms are forced across the boundary into the dilute phase. This movement is endothermic, meaning it must absorb energy to occur. By pulling this heat directly from the surrounding environment, the process acts like a microscopic vacuum, cooling quantum chips to the extreme temperatures required for breakthrough computation. As we scale quantum systems, we hit a massive physical wall, the wiring bottleneck. A modest 100-qubit processor requires hundreds of coaxial lines, each acting as a highway for unwanted heat. To protect the quantum state, we must meticulously anchor these wires across extreme temperature stages, down to nearly absolute zero. Balancing signal integrity with thermal management requires precise attenuation and amplification. Solving this complex engineering challenge is vital for the future of large-scale quantum architecture.
Welcome to Layer 3, the classical conductor. This is where we bridge digital logic with quantum physics. At its heart, the pulse processing unit orchestrates millions of operations every second, converting digital commands into precise microwave pulses to manipulate qubit states. Simultaneously, the readout chain captures incredibly faint quantum signals, amplifying and digitizing them to determine a final 0 or 1. This creates the high-speed, closed-loop feedback system, vital for reliable quantum control.
In quantum computing, speed is our greatest defense against decoherence. Because quantum information decays so rapidly, we must execute a complete error correction cycle within a mere 10 microseconds. By leveraging heterogeneous compute, we link quantum pulse units directly to classical GPUs via ultra-low latency interconnects. This allows us to decode complex error syndromes and stream corrections in real time, effectively outrunning qubit decay to ensure stable, reliable performance for the most demanding applications. Moving from a developer's idea to physical quantum execution is a journey of refinement. It begins with high-level Python algorithms that define complex problems. These are compiled into logical circuits using specialized frameworks, then translated into machine-level instructions that map specifically to a chip's physical qubits. Ultimately, this digital logic is converted into precise analog microwave pulses. These pulses enter the cryostat, directly interacting with matter to perform the actual quantum computation. The quantum programming landscape is currently defined by three major ecosystems. IBM's Qiskit is the most widely adopted, utilizing AI-enhanced transpilers to optimize code for specific hardware. In contrast, Google's Cirq is purpose-built for the NISQ era, offering specialized abstractions to manage hardware-specific noise and constraints. Finally, Rigetti's Forest ecosystem focuses on the future of hybrid computing, using shared memory architectures to seamlessly integrate quantum and classical processing for high-performance execution. Since physical quantum processors remain a scarce and expensive resource, quantum simulators are essential for modern development. They allow us to test and optimize complex circuits on classical hardware before deployment. Platforms like Blue Qubit leverage NVIDIA GPUs for high-speed, large-scale experiments with seamless framework integration. Meanwhile, tools like Rigetti's Quantum Virtual Machine provide high-fidelity simulations by incorporating realistic noise. These simulators create the vital playground needed to refine the algorithms of the quantum future.
We're moving toward a hybrid era where quantum computers don't replace classical systems, but rather supercharge them. Imagine a tightly coupled fabric where a central orchestrator intelligently routes tasks based on their specific complexity. Your CPUs handle database logic, GPUs power your AI, and QPUs tackle the hardest combinatorial math. This quantum-centric architecture ensures every algorithm is parsed to its ideal hardware, creating a seamless, high-performance ecosystem for the next generation of scientific discovery. To build a functional quantum computer, we must orchestrate 4 distinct scientific domains in perfect, microsecond harmony. It begins with the software layer, translating human logic via classical GPUs. This integrates with specialized hardware providing real-time feedback loops. To function, we need a cryogenic layer that freezes out the universe's thermal noise, creating the extreme environment where the quantum layer can finally perform the impossible. It's more than a device, it's the absolute mastery of physics.